So in the previous session, we were modeling the isolated square footing. So we have done multiple steps. Initially, we have worked with the modeling part, and then we have assigned the load. We have done the modeling of columns, modeling of footings, and then we have assigned soils upgrade properties. And finally, these are the steps that we have completed in the last session. Now, in this particular session, we are going to do the remaining part, which is basically the analysis part. And then we will work with a couple of other options that we can do with the analysis and modeling and analysis of modeling, design and analysis of square foot. Right. So this is what I have done in the last session. Maybe you also have the same thing. So open the model that you have currently that you have done previously. And now what we are going to do is we are going to run the analysis. So modeling part is completed. So the next thing is we need to do the analysis part. So how to do the analysis? So in order to do the analysis, here you can see there is a play button. Okay, there is a play button here. So that is basically meant for analysis part. So once you click on this one, automatically the computer or the software will ask you to save the file that is available. So if you have already saved, it will not ask. If you haven't saved, it will ask you to save the file. And once only after you save the file, then only the analysis will be completed. Okay. So currently I have already saved the file. So let me click on analysis here. You can see run analysis and design. Click on that. Or you can also see there is one more option in the menu bar that is called as run. So even here also you'll find run analysis and design. You can see here run analysis and design. So just click on any one of the option run and click on. So once you complete this, what will happen is it will show you the analysis part. So here, in order to see the analysis, instead of keeping yourself in the 3D view, it's better if you keep it in the XY plane. So let me keep it in the XY plane. So just click on XY. And if you zoom it, you will understand the analysis part. So this is your analysis. Now we need to interpret this analysis. So you can see there are some blue color lines and then light green, dark green, and then some kind of green, and then yellow at the middle, and then red at the center, something like that it is there. And in the left pane, in the right pane, if you observe, there is some scale that is visible here. Okay, you can see a scale over here. So we need to interpret these colors with this scale. Okay, we need to interpret these colors with this scale. So I'll talk about this scale in some time, but let us have an understanding of what we need to do now. So the first thing is, whenever we do the analysis, okay, once we complete the analysis, we will get these color combinations. So usually for the design of footings, we have four important steps. Okay, for the design of footings, we'll have four important steps. So let me write that. So for design of footings, we will have the following steps. So let us see what are those steps. So the first step is finalizing the in-plan dimensions. Finalizing the in-plan dimensions. So what does it mean by in-plan dimensions? In-plan dimensions of footing. So what does it mean? In-plan dimensions are nothing but length and width of the footing. Okay, length and width of the footing. So we already have the length and width of the footing. In manual calculation, we got the length and width, that is 2.8 meters. Even in Excel also, we got the length and width of the footing. You can see here. Okay, length here and then width of the footing. Right. So we have got the length and width of the footing. And here currently is we have finalized the dimensions, so that is length and width of the footing using Excel sheet and manual sheet, using Excel sheet and manual calculation. But how can we validate which result is correct? You should know whether the software result is correct or software result, you keep it aside. Currently we are not going into the software result. So first we need to understand which result is correct. Either Excel sheet result is correct or the manual calculation result is correct. So we need to validate this one. So that's our next part, that is validation of results. Right. And the second step is we need to decide the depth of the footing. Okay, we already have decided the depth of the footing both in Excel sheet calculation and manual calculation. So we have assumed the overall depth as 600 mm, and then we have went for the calculation of one-way shear, two-way shear, and reinforcement. The same we have done in the Excel sheet also, right? But here the question is whether the depth of the footing is safe or not. That also we have to check. Okay, whether the depth of the footing is safe or not. So we need to validate this also. Okay, with this one also has to be validated. So that's validation of result. That's the second one. And the third one is we need to do the reinforcement design. Okay, we need to do the reinforcement design. Till now, we have not talked about the reinforcement value. So we need to do this reinforcement design. And finally, the last and most important step is we need to check whether settlements are within the limits or not. Okay, settlements are within the limits or not. So we know that the maximum allowable settlement in any type of footing is 25 mm. Okay, maximum is 25 mm. So we need to know whether in the software whatever we have calculated, is it less than 25 or greater than 25? If the settlement value in the software is less than 25, then settlement criteria is C. If it is greater than 25, then we need to do the modifications accordingly. Right. So first let us come with the first one. What is the first one? Finalizing the in-plan dimensions of the footing. So what does it mean by in-plan dimensions? Length and width. So how to finalize or how to validate the in-plan dimensions of the footing? So in order to validate that, just go to save. And here you can see at the top, there is this option called show reaction forces. You can see here, show reaction forces. This option is called as show reaction forces. Let me keep show reaction forces. So once you click on show reaction forces, a dialog box will get popped out. And what is our load case? Have we designed in the dead load combination or in the live load combination? We have designed in the live load combination. Okay, we have designed in the live load combination. But here, load combination is important, not load case, load combination. Because we know that in our structures, we always have combination of loads. We don't have only dead load or we don't have only live load. We always have load combination. So check load combination here. So we have already decided the load combination, that is dead load plus live load. So we don't need to go for the factored load. We need to go for the service load criteria only. Okay, when you are finding out the reactions, service load criteria is sufficient, right? So check the load combination and select dead load plus live load, and then what type of reactions we want to see. So basically, we want to see the soil pressure. Okay, we want to see the soil pressure. So just click on soil pressure and then display contours on deformed shape. So select this option so that it will display the contour lines. And once you click this one, select scaling as automatic, minimum and maximum as 0, 0. And then click on apply. Once you click on apply, you can see there are some contours that are representing here. Can you see the contours here? So contours are being represented here. And you can see the different color pattern. Now here we are considering service load combinations. Okay, what does it mean by service load combinations? Dead load plus live load. Instead of factored load, we are considering the service load combination. Because what is the reason for that? The reason is SBC of soil is already a factored load. Okay, whatever the SBC of soil we are considering, that is already a factored load. Now, if you move your cursor to the center point, okay, if you move your cursor to the center point, you can see the upward soil pressure. What is upward soil pressure here? Can you see the value? Minus 197.71 kilonewtons per square meter. That is basically the upward soil pressure. Now we should know whether this upward soil pressure is within the limits or not. Okay, whether this upward soil pressure is within the limits or not. Now let us check before this one. Let us check whether the same upward soil pressure we got in the manual calculations or not. Let me go to the manual calculation. Now in software, we are seeing the upward soil pressure at the center. So we should not look at corners. We should always look at the center. Why? Because at center only maximum pressure will be there. So at center, the maximum pressure is 197.71. But when you come far away, okay, when you come far away from the center, the upward soil pressure will get reduced. Why? The maximum pressure will be there only at the center of the footing. At corners, there won't be much pressure. Okay, there will be pressure, but that's not an influential factor. Right. So here in the software, we got the upward soil pressure as 197.71. Okay, minus 197.71. Now let me go to this Excel manual calculation And here you can see upward soil pressure. What is the value? 196.43. That is Excel manual calculation. Even in Excel also it is the same thing. Let me check. Right, you can see here 193.57. Okay, in Excel, in software we have, in manual we have got 196. In, let me write that. So in manual we have got 196.43. This is manual calculation. In Excel we got it as 193.57. Okay, in Excel we got 193.57, and in software, let us check what is the value. It is 197.71. Okay, in software it is 197.71. Now here you can see three different values we are able to see. Okay, three different values we are seeing. Now which one is correct? So here you can see all the values are within the ranges only. So there is no much change here. So when there is no much change, you don't need to bother about that. But still, what is the reason behind the difference between the values of manual calculation, Excel calculation, and the software calculation? The reason is in manual design. Okay, in manual design, we have not considered, let me go here. So in manual design, we have not considered the self weight of column. We have considered the self weight of footing. What is self weight of footing? 10% of column load. But in manual calculation, we have not considered the self weight of column. But how will you calculate the self weight of column? Self weight of column equals to the dimensions of the column multiplied by unit weight of RCC. What is the dimension of the column? In our case, the dimension of the column is 400 by 400 mm. You can see here. Okay, 400 by 400 mm, and the height is 3 meters. That is what we have considered. So height of the column dimension is 0.4 into 0.4 into the height. What is the height of the column? 3 meters into unit weight of RCC. So that's how you can calculate the self weight of the column. So if you solve this one, you're going to get the value as 12 kilonewtons. Okay, this is the self weight of column. So length and width of the column multiplied by height of the column multiplied by unit weight of RCC, right? But whereas in Excel, okay, if you go to Excel, there will be a gross load. Here you can see, okay, there will be a gross load here. What is the gross load? 1517.60. Sorry, there was some mistake. Right. So here the gross load is coming. But in this gross load, have we considered the self weight of the column? No, we have not considered. So in Excel, the gross load is 1517.60. But whereas in manual calculation, we have not considered the self weight of the column. So we need to consider that self weight of the column also. But in any textbook, whatever textbook that you refer, in any textbook, we don't see the consideration of self weight of the column. We directly consider only the footing. So that's the reason why we are seeing three different values. Let me explain you that. So the total load will be 1517.60. Okay, 1517.60 plus 12 kilonewton. So that will become 1529. Yeah, 1529.60 kilonewton. This is slow. Now pressure, upward soil pressure. Okay, upward soil pressure equals to the total load. Okay, sorry, it is 1529, not 1229, 15. So upward soil pressure equals to 1529.6. Okay, 1529.6 upon the size of the footing. What is the size of the footing? It is 2.8. You can see 2.8 length and width of the footing is 2.8 by 2.8 meters. So 2.8 into 2.8. So when you solve this one, okay, so when you solve this one, you will be getting, let me check that. Even I'm not sure what is the value. So let me open calculator. Right. So here the calculation will be 2.8 into 2.8. Let me check first with that one. That is 7.84. So 1529.6 divided by 7.84. Sorry, 7.84. When you solve this one, the value is 195.10. Okay, the value is 195.10 kilonewtons per square meter. Okay, kilonewtons per square meter. That's the upward soil pressure. Now here, when you go into the software, okay, in software, what is the value that we are getting? In software, the value that we are getting is 197.7. Okay, 197.7. So here, if you check down the value, whatever the value that we are getting here, that is almost close, just the 2 kilonewtons per square meter. That is almost close to the software calculation. Okay, that is almost close to the software calculation. That's the result. That's the reason why we are seeing a difference in values. Okay, I hope you understood why the difference is being seen. So the reason is when we are working with the manual calculation, we don't consider the self weight of the column. Okay, we don't consider the self weight of the column. So if you consider the self weight of the column, then the results will be almost similar. There won't be any problem. So that's how you can validate results. So hence, manual results and CSI safe results are validated. Okay, they are almost close, so there won't be any problem. Right now, if you move the cursor in CSI safe, let me do one thing. Let me close this one. Yeah. So if you move the cursor, okay, if you move the cursor to this towards the end of the footing, you can see what is happening to the from center. The value is 197.71. Now, what is happening to the upward soil pressure when I'm going away from the center? You can see the value is getting reduced. Okay, the value is getting reduced. So here the values are getting reduced. So at corner, what is the value? If you go to the corners, the value is 193.38, and at somewhere in here it is 194. So it is almost fine. Now the question is how to know whether this upward soil pressure is within the limits or not. The condition for that is the upward soil pressure should be decided whether it is within the limits or not. We should remember one condition, which is upward soil pressure. Okay, upward soil pressure must always be less than SBC of soil. Okay, upward soil pressure must always be less than SBC of soil. What is the software value? It is 197.71. Now, what is the SBC of soil? If you go to the calculation, here you can see SBC of soil is 200 kilonewtons per square meter. So is it safe or not? So upward soil pressure is less than SBC of soil. So that means it is safe. So here, one more thing that you need to understand is what is that negative value represents. You can see minus 195, minus 194, minus 197. What does that negative indicate? Suppose if the force is acting downwards, okay, when the force is acting downwards, usually whatever the loads that are coming, all the loads will be acting downwards only. So if the force is acting downwards, the upwards will be the soil pressure. Okay, if you remember the concept, the simple concept, if you take a simple beam, now this is actually the load. So when the load is acting downward, the force will be acting upwards. Okay, the force will be acting upwards, and this is called as upward soil pressure. So if the upward soil pressure, okay, if the upward soil pressure is less than the force acting downwards, okay, if the upward soil pressure is less than the force acting downwards, there will be the settlement in the mass. Okay, suppose if you consider the downward force as x and upward force as y. So what I am telling? If the upward soil pressure, that is y value, if the upward soil pressure is less than the force acting downwards, that is x. So if the upward soil pressure is less than the force acting downwards, then there will be a settlement in the foundation or settlement in the soil mass. Now, what will happen if the values are positive? Now here you can see the values are negative. Now, what if the values are positive? If the values are positive, okay, if the values are positive, then there will be settlement in the soil mass. Remember that. If the values, sorry, not settlement, uplifting. If the values are negative, settlement will happen. Okay, if the upward soil pressure, if the upward soil pressure is negative, okay, there will be settlement. Okay, there will be settlement in the soil mass. Now, what will happen if the Upward soil pressure, if the values are negative, so if the upward soil pressure is positive, okay, let me write that. If the upward soil pressure is positive, then what will happen? There will be uplift in the soil mass. Okay, uplift or tilting will happen. Uplift or tilting will happen in the soil mass. So that's the condition that you have to remember. Okay, so we should always get the negative soil pressure only, not the positive soil pressure. Why? We can have the settlement, but we should never have, or any foundation should never experience the uplifting or tilting portion. Remember that. So the values of upward soil pressure should always be negative. That's one thing that you have to remember. Now, till the settlement is equal on all the sides, there won't be any problem to the foundation or to the structure. If the settlement is uneven, then there is a problem. If there is an equal settlement, suppose if you take the footing slab like this or foundation slab like this, if the settlement here is 5 mm and if the settlement here is 5 mm, then there is no problem. Suppose if the settlement somewhere here is 7 mm and if the settlement somewhere at the end is 1 mm, then there is a problem. Okay, this is non-uniform settlement. Till the settlement is equal on all the sides of a footing, there won't be any danger to the structure. That you also remember. Now, the next thing is, let us check the settlement. Okay, let us check the settlement. I'll talk about this one. Depth and reinforcement we'll see in the later cases. Let us check the settlement. Now, what is the maximum settlement or allowable settlement? It is 25 mm. Now, let's see whether the footing that we have designed is having, let me close this one. Well, let's see whether the footing that we have designed is having within the settlement limits or not. That is, it should be less than 25. Now, how to see the settlement values? So in order to see the settlement values, you can see this option, which is called as show deformed shape bars or show deformed shapes. Let me show you that. So you can keep the cursor here. You can see show deformed shape. So just click on show deformed shape and a dialog box pops out. And here also we need to look for the load combination. So select the load combination, and in our case the load combination is dead load plus live load. And check automatic and draw contours. Okay, check draw contours and then click on apply and close. Now, if you move the cursor to the center, now what is the settlement that you can see? Minus 24.71. Why minus? Because settlement happens in the downward direction. That's why minus. If it is in the upward direction, then it will be plus. So upwards, if it is happening upwards or positive, that means uplifting is happening. If you are seeing negatives, that means settlement is happening. Now, can you see what is the settlement value? Minus 24.71. What is the allowable settlement? Allowable settlement is 25 mm. Is it within the limits or not? Yes, it is within the limits only. So that means settlement is also safe. Now the question is, if settlements are beyond the limits. Now in this case, we are getting minus 24. Now let's say if it was minus 27, then what we should do? We should know that also. So if you are getting minus 27 or minus 27.7 mm, something like that, more than the allowable settlement, then what we should do? What kind of parameters we should modify in order to limit the settlement? So if settlements are beyond the limits, let me write that. If settlements are beyond the limits, okay, if settlements beyond limit, what we do is we have the dimensions. Okay, to modify the dimensions accordingly. So dimensions of what? Dimensions of footing. So that means we need to change the length and depth of the footing. Okay, we don't need to go for the width of the footing. We always need to modify the dimensions only length and depth. So you have to do trial and error method for that. So once when you practice more and more problem statements, then you will understand. So once after I complete this isolated square footing design, I'll give you a couple of problems so that you can try it out. Right. So if settlements are beyond limits, we have to modify the dimensions, especially the length and depth of the footing. Now, what if upward soil pressure gets failed? Okay, if upward soil pressure, if upward soil pressure gets fail, then what we have to modify? Okay, then modify in plan dimensions. Okay, in plan dimensions of footing. What does it mean by in plan dimensions? Length and width. Okay, length and width of the footing. Suppose we'll talk about punching shear, that's two-way shear. If punching shear gets failed, that's the next one. We'll check that. If punching shear gets failed, then what we have to do? Then modify the depth of the footing. Depth of the footing. So these three conditions you should remember because these are very much important. Right. So now let us check the here. Punching shear is nothing but two-way shear. Okay. So that's our second step. So whether the depth of the footing is safe or not. So we have completed the first one. Okay. And then we have completed the last one. Now let us look at the second one, whether the depth of the footing is safe or not. How to know? In order to know whether the depth of the footing is safe or not, we have to check the punching shear. That's also called as two-way shear. Now, let's say we have a footing and a column. Now, why we are the reason for providing the footing to a column not needed to provide the footing slab if the soil is having enough shear load carrying capacity. Okay, if you observe this one, so we have a column, and for the column we are providing the footing. Now, why we are providing footing? Because the soil, whatever that is there at the bottom, it will not have enough shear capacity. If the soil is having enough shear load carrying capacity, in such cases, we can directly provide the column on the ground itself. Okay, we can directly provide the column on the ground itself. To consider this scenario, if you have ever went into a hilly areas, okay, on the surface, on the sliding surface of the hilly areas, there will be many houses that will be constructed. Okay, if you go to any hilly zones or hilly areas, you can still see the houses that are constructed in the on the sliding surface of the hills. So in these cases, they must not have made any kind of footings here. Okay, they will not go for footings here. What is the reason? Because this is a rocky strata. The hill is actually a rocky strata. When there is actually enough safe bearing capacity or enough load carrying capacity, why we need to dig the column? Why we need to dig for footing? There is no requirement. So in that cases, we can directly place the column by digging a smaller depth of the rock, and then we'll provide the column directly. Okay, so the shear resisting capacity will be very good there. So for that reason, we will not provide wherever we have enough shear load carrying capacity. We don't need to provide. Okay, we can provide, but we don't need to provide the footing there. We can directly place the column in the ground itself. That is on the ground. I mean the rocky strata or the strong area. So mostly in hilly rocky areas, we directly provide columns after making a small excavation on rock for connectivity purpose. That's the thing. Okay. Now, what is meant by punching shear? Okay, that's the next question. So I'm telling that punching shear is there. So what is this punching shear? Suppose if you take a column, okay, if you take a column which is attached to a footing or a foundation slab. Now, if you take this one, how column will get cracked? So the column cracks will happen something like this. It will happen at a 45-degree angle. Okay, something like this, it will happen. These are column cracks. So if more load comes onto the column, then these cracks will happen at an angle of 45 degrees. So now here the thing is this portion, whatever the portion that is there here, this portion will not be the cracked portion. Okay, whatever thing that you see here, this one, okay, that is inside the crack, this portion is actually not getting failure. Which is getting failure? It is this portion. Okay, it is actually this portion that is getting failure. Let me show you that. So this portion of the footing is actually getting failed. Okay, so whatever the blue color one that you are seeing here, this is actually a very stiff portion. There won't be any problem with this for this area. And this area is called as stiff area. Okay, this area is called as stiff area. Why I'm calling this a stiff area? Because this portion will never get failed. This will always be same. The only thing that gets failed is the sides of the footing. Okay, once after cracks forms here. Okay, this portion will get failed, and this side also this portion will get failed. So why cracks are initiated from corner junction of column and footing? The reason is the load transfer will happen exactly at this right. Now, when the load transfer happens in an indirection way, suppose if the load transfer happens in this way, or if the load transfer happens in this way, then cracks will initiate. Now, when the load transfer will happen in this way, when you don't properly design the column in an for an exact load carrying capacity. If you have designed an eccentric column, or if you have designed an uniaxial, biaxial column. Suppose let's say you have to design an uniaxial column. So instead of uniaxial column, you have designed a biaxial column. Then in that case, load distribution will not happen properly. So when the load distribution doesn't happen properly, then cracks will initiate at an angle of 45 degrees from the corner, this one, from this portion of the foundation slab, or the connectivity between the foundation slab and the column, this portion. Let me write that. From this corner portions, the cracks will initiate. Now let's see the punching shear. Okay, let's check the punching shear. That is two-way shear. So if you go to CSI Safe software, and here, if you see this particular option, let me highlight this one, this one. Okay, if you see this particular option, this is called as show punching shear design. That option is called as show punching shear design. Let me keep the cursor there. You can see show punching shear design. So just click on show punching shear design, and directly you will get the value. Let me click on that. And now can you see the value? 0.4638. That's the value. Now, how to know whether the punching shear, whether the two-way shear is safe or not? Always remember, the punching shear value should always be less than 1. Okay, if the punching shear value is less than 1, then it is safe. Then there is no problem with the punching shear design. Okay, 99.99% of the times, the punching shear value will always be safe. There won't be any problems. Okay, there won't be any problem. But by chance, if you are getting greater than 1, there might be one thing that you will be missing. What is that? Let us check that. Most of the times you will get it, but if you are not getting, there must be one problem. So currently I'm getting 0.4638, which is less than 1. But I'll tell you what will happen. What could be the reason if the punching shear is greater than 1? The reason is the code book might have considered, the SAFE software might have considered a different code book. Let me show you how to check that. So just keep the cursor at the center point. Okay, you can see a circle there, a red color circle. Just keep the cursor there, and then right click. Once you right click, now here you can see what is the code that it is showing here currently. It is showing me IS 456 2000. Okay, it is showing me IS 456 2000. Now here you can see IS 456 2000. Now, if you see any other code book other than IS 456, that means it's a problem. Okay, that's where the problem occurred. That is one reason. Okay, if you don't see IS 456, then it's a problem. That means it has calculated the punching shear according to some other code book. Let's say ACI code book, or European Union code book, or some local Australian code book, whatever the countries are. So that is one thing why you might be getting the punching shear greater than 1. Now, if you get the punching shear greater than 1, how to change this IS code? Okay, how to change this IS code? Let's change the design code. Here it is IS 456 2000 only. There is no problem. But let me change it for your convenience. I'll just show you that option also. Right. So just close this one. Okay, close this dialog box. Right. Now, before changing the code book, first you need to unlock the model. You can see the unlock symbol here. Click on unlock. So only after unlocking, then once you do unlocking, what will happen is all the results will go. Whatever the analysis, whatever the results that you have done so far, all the results will get disabled. You will not see the results again. So just unlock the model. You can see unlocking the model will delete analysis and design results. Okay, let it get deleted. No problem. We'll do the analysis once again. We can run the analysis one more time. Right. So click on OK. Right. So analysis is not, you don't see any values here. Can you see any values? No, nothing. Right. Now go to design. Okay, go to design, and then go to design preferences. Once you click that, a dialog box appears, and here you can see design code. Make sure to check the IS 456 2000. Okay, make sure to check the IS 456 2000. And then minimum cover to the slabs. Check steel factor of safety and concrete factor of safety, and cover to the slabs. What is the cover that we have considered? It is 50 mm. So give the cover also as 50 mm only. Right. So cover as 50 mm and bar size. So here we should not give, what is the bar that we have considered? 16 mm. You should not give 16 mm. You should give half of the bar size. Why? When it is calculating the effective depth, it will calculate from, if you consider this as the diameter of bar, effective depth will always be calculated from the center of the reinforcement bar. That means 8 mm. So make sure of giving this one. So here it should not be the original diameter, it should be half of the diameter. So give the bar size as 8 mm. So what is the reason for bar size is taken as 8 mm? Because the original diameter is 16 mm, and to calculate effective depth, we should consider half of the diameter of bar. So hence 8 mm is taken. So select, make sure of checking this one and then click OK. Right. So that's one thing. And then the next one is design combinations. So just click on design combinations or combos, click on that. And here the load combination type. So make sure to keep it as strength ultimate. Don't keep any other ones. Make sure to keep it as strength ultimate. And then the list of load combinations. Okay, list of load combinations and design load combination. Now in the design load combination, you should have 1.5 dead load plus live load, and the list of load combination, you should have dead load plus live load. Make sure of these ones also. Design load means 1.5 times of load. Service load means just loads, that is dead load plus live load. Right. So make sure of selecting this one. So these are the two steps. What is the first step? First step is to change the code, change the clear cover, both top and bottom, and change the bar size. Make sure the bar size should not be the original one, but the half of the original diameter. And the second one is this one, load combination type, which is strength ultimate. And the list of load combination, you should have this one, dead load plus live load. And here you should have design load combinations as 1.5 times of dead load plus live load. Right. Just click on OK. Once it is done, just run the analysis once again. So let me run the analysis once again. Click on the play button and you can see the analysis here. Now also you can check whether the upward soil pressure. What is the upward soil? Sorry, not the upward soil pressure. Let me click on upward soil pressure. This icon here. This is for upward soil pressure. So let me click on that to get the upward soil pressure. Click on that. And here the load combination is dead load plus live load. Soil pressure you have to check. Display contours and deformed shape. Minimum maximum is 0. Apply. Close. Now you can see 197.71. Okay, 197.71. What is the calculated value here? 196. So it is almost same. Okay, it is almost same, right? So now the next thing is you can see 197.71 and the value gets reduced when you go far away, right? So now let us check the other factors. Now the other option that we need to look after is this one. Okay, the other option that we need to look after is this one, which is, let me show you, which is show deformed shape. So just click on show deformed shape. Okay, click on show deformed shape, and then the load combination, okay, should be dead load plus live load. Select automatic, minimum maximum 0, draw contours, let it be like this, and then click apply and close. Now if you move the cursor to the center, the value is minus 24.71, which is settlement value. So what is the allowable settlement? 25 mm. What is the settlement that we are getting? 24.71. So it is within the limits only, no problem. Now just keep the cursor at the center. Okay, keep the cursor at the center and then right click. Right. So once you done with this one, so you can see the assignments, geometry, loads, and then design. So all the values you can see, now all the parameters you can see. Now here, combination. Let me just show you one thing. Let me close it here. Just keep the cursor at the center and then right click, right. So here, loads, okay, you can see the load pattern is live load and then load along X direction, Y direction, everything. That is dimensions of the footing. The total load you can see, that is 1400 kilonewtons, right? So that's how you can check the factors. Okay, so the other parameters, right? So that's the one part. Now, the next thing is, or the next thing that we have to look after is, let's check the punching shear design. Let me click here. How to check punching shear design? So this is the option. Okay, just click on that. Click on punching shear design and you can see the value 0.4972. That's also fine. Right. Now just keep the cursor at the center, right click and make sure you should have IS456 here. Okay, make sure you should have IS456 here. Right. Now there is one more thing. So I told you how to change this IS456. That's the first one. I was telling that there is also one more parameter that could be influencing the punching shear value. What is that? So you can see all the geometric properties here. Can you see all the geometric properties, combination, point label, and then column shape, column location, global coordinate X, global coordinate Y. That is all fine. Now, one thing that we have to bother is the column location. What is the column location here? What software has considered? Software has considered that it is a edge column. What does edge column represent? If you consider this as your site area, okay, if you consider this as your site area, column is there somewhere in the edge portion. It can be in the any edge, maybe this edge, whatever the edge. But have we mentioned to the software that column is there at the edge of the boundary line? No, we have not mentioned. So usually whenever we design the columns, we should always design the columns in such a way that they should be at the center. Okay, they should always be at the center. So if you draw a footing, always footing should be, the column should be there at the center of the footing. That's one thing. So, but here what is the consideration? It is considering edge. So that is also one of the reason why we are getting the difference in values. So 296, 496 or 296, 297, something we are getting, right? So that difference is because of this also. Okay, so column location equals to edge is seen here. What does it mean? It means the average effective depth of the slab. Okay, if you consider the effective depth of the slab, that equals to overall depth of the slab is 600 mm. Okay, clear cover we have taken it as 50 mm, and the diameter of bar is 16 mm, that is 16 by 2, that is 8 mm. So if you solve this one, you're going to get 542 mm. This is the effective depth of the slab. Okay, effective depth of slab. Now, what is the effective punching perimeter? You can see here 4684.5. So where the punching shear is acting? Punching shear is acting in this area. Okay, in this dimension. But in Excel calculation, let me show you that. In Excel calculation, effective punching, let me check that, where it is. Let me check that. Yeah, here you can see. Perimeter length of shear area. What is the perimeter length of shear area? It is 3768. Okay, this one we have not calculated in the manual calculation, so it is directly coming here. Okay, 3768 mm. So there is a difference between the Excel sheet calculation and the software calculation. What software is telling? 4684. What Excel sheet is telling? It is 3768. So there is almost 1800 something change is available. Why this change is seen? So there is a difference between Excel and manual Excel and this software calculation. What is the reason for that? Now we need to understand that reason. Let us check that reason. So to understand that reason, let me keep it here. Yeah. To understand that reason, we know this is the footing. Okay, this is the footing. And inside this, we have the column. Let's say this is our column. Now, what is the punching shear? Punching shear acts at a distance d by 2 from face of the column. So let us consider this is our punching shear perimeter. Okay, it is acting at a distance d by 2 from face of the column. Right. So this is basically the width of the column. Okay, this is B, that is width of the column, and this is A. Let me call it as A and B. That is what we have considered. Right. Along all the sides, the value is d by 2. Okay, this side it is d by 2. That is punching shear area. So from d by 2 from face of the column. Now, if you consider the length, okay, if you consider this length, what is the value? D by 2 at the top, okay, D by 2 plus B plus D by 2. Okay, if you talk along the y-axis, so D by 2 plus B plus D by 2. Okay, D by 2 plus D plus B plus D by 2. So what does it mean? It means B plus D. D by 2 plus D by 2 is D, so B plus D. So what is B? B is the size of the column, that is 400 mm. What is the effective depth? Effective depth is 542. We just have calculated. Okay, so this is 400 plus 542, which is 942 mm. Since it's a square column, on the other side also it is same. That is D by 2 plus A plus D by 2. So 400 plus 542, it is 942. What is the perimeter value? Perimeter will be 4 times. It's a square column. 4 times of 942. So what is 4 times of 942? It will be 3768. Okay, 3768 mm. But in software, what it is taking? it is taking some 4,000 something. Let me show you that. Okay, I have closed that one. I think it was 4,000 something, 4,000, 4,600, 800 something like that. So let me show you anyway. Let me check it here. Yeah, so 4,684. You can see the value here. But how much we are getting? 3,768 mm. So we have to correct the value in software. Okay, we have to correct the value. So it is taking some additional punching shear area. Why this additional punching shear area? It is because while calculating, it is taking it as an edge. But originally, the column is lying at the of the footing. Right now, this one. Let me show you that. So in order to change that one, just click on 3D. Let me go. Let me zoom it. Right. Just click on 3D. Okay. Right. You can see here. Click on 3D. Now select the bottom joint. Okay. Select the bottom joint of the column. So let me clear section. Here it is doing 2 points selected. Right. So select bottom joint. You can see at the right side. Sorry, at left side one. Right. So now what we have to do is we have selected the bottom point. Now go to design. Okay, there is this option called punching check overrides. Design, you can see punching check override. So we have to overwrite the value. Why? Because there is a difference in perimeter value. So click on punching check overrides, and then here you have to punching check punching shear. It should be program determined, and this is where we need to change location type. See what it is taking. It is taking automatically. So automatically, auto means it is considering edge. Now we have to change this to center or interior. Not center, it will be like interior. Let me show you that. So click on this drop down and you can see here, interior, right? So click on interior and then click on OK. Okay, click on OK. And it is telling that design results will be deleted. Let it get deleted, no problem. Click S, right? Now, once again, run the analysis. So run analysis. So once the analysis is run, just click on go to XY plane. Okay, so check punching shear. Okay, you can see 0.487. Right. Keep the cursor at the center, right click, and here you can see what is the location. Earlier it was edge, now it is interior. You can see here. Now it is interior. Right. So now what is the effective punching shear punching perimeter? 3768. What was the earlier value when we are calculating? It was also 378. Okay, so it was 4 times of 942. That is what we got. Okay, so 4 times of 942 is 3768. So that's how you have to validate the results. Okay, that's how you have to validate the results. This is all about the analysis part. Now, what is left over? The second step, second or third step, which is that. Let me check that. The third step, the last part, design part. So what we need here, we need the reinforce. Okay, we need to design the reinforce. So far, whatever checked, upward soil pressure we have checked, punching shear we have checked, and settlement also we have checked. Things we have checked. Upward soil pressure, punching shear is nothing but two-way shear, and the settlement. Now, what is left over? The leftover is one-way shear. So, when you do one-way shear, then only you will get the reinforcement design. Okay, when you do one-way shear, then only you'll get the reinforcement design. Now, to check one-way shear, we need to know the percentage of reinforcement. Okay, to know one-way shear or to calculate the one-way shear value, we need to know the percentage of reinforcement. If you remember, in the manual calculation, we have calculated PT. Okay, PT. So this value you have to calculate. So where we have to calculate at a particular section, whichever section, wherever you want to provide the reinforcement, at that we have to, at that particular section, we need to know the percentage of reinforcement. Hence, without knowing the percentage of reinforcement or without knowing the value of PT, we cannot find or we cannot check one-way shear as we haven't done the reinforcement design. Okay, so the reinforcement design that we will see in the next session. Why I'm telling it in the next session is I have to one more time I have to redesign this one, remodel this entire one. Okay, modeling has to be done again. So I'll tell you what correction we can do. That I'll tell you in the next session. Right. So that's from my end for this particular session. If you have any doubts, you can unmute and ask the doubts. Thank you.